Okay, so we're going to look at quiz 5, problem 2. We talked about the theory behind this in tutorial, and so we're actually going to look at the solution here. Because as I speculated, there was a pretty particular solution that we were looking for. So we'll sort of review the concept as we look at the actual solution. So the idea was, so first of all, what's the question? We want to approximate or estimate the third root of 4 using 2 different linear approximations. And the wording was, said 2 different initial points. What this means, so the first question is what do we mean by approximate it using linear, or estimate using linear approximations? Linear approximations here means tangent lines. What we're doing, I'll just come down here and review quickly the idea. What we're doing is using the fact that the tangent line is the best linear approximation. We talked about this in tutorial. The best linear approximation of a function near a point. So when we're close to a point, it's going to be the best linear approximation. And in fact, as we talked about as well, if you zoom in on the tangent line, the line that touches at only that one point, so this is A, this is f of A, and this is the tangent line at that point. The tangent line to f at the point A, it's a function of x, and its equation is f prime of A. We're going to need this for the problem. It's f prime of A times x minus A plus f of A. And this incorporates the fact that the slope is the derivative at the point, and it passes through the point A f of A. So when x is equal to A, this is going to be 0, and the value of the function will be the f of A that pops out there. So what we're doing with this problem is saying, well, because the graph flattens out against it really close to there, if I go a little bit to either side of A, so if I go a little bit to the right or to the left, so I go to here, this is A plus H, and I go up to this point, this is f of A plus H. Well, what's called the increment, so I'll do it in a different color here. Actually, I should do it in green because that thing is green. The increment, so the change in the function, which is, this is f of A plus H minus f of A, right? That's f of A. This is approximately equal. I'll do the neutral sort of blue color for the squiggly equal sign. That means approximately equal, by the way, when you have an equal sign with that squiggly line above it. This is approximately equal to, and what color should I do this in? Maybe purple. This is approximately equal to delta x times f prime of A. Or in this case, if this change in x, this is the delta x, which is the h, it's how much we've gone to the right. If we're calling it h, then that means that this thing is squiggly equals 2h times f prime of A. And this is of course for small h or delta x, right? And this is where the definition, the limit definition of the derivative comes in, right? Saying that the limit as h goes to 0 of f of A plus h minus f of A over h is f prime of A. Well, this is saying that there's no limit to how close I can get that quotient, the slope of the secant line, right? So the secant line from A to A plus H, if that's A plus H. The secant line would be this, right? This triangle is actually the triangle that shows us the slope of that secant line, and that's this quantity. right? We get the derivative, the f prime of a, at the point by taking the limit as h goes to 0, letting h get arbitrarily small. And and that limit existing is saying that this is a number, right? The f prime of a, that number is the unique number, such that there's no limit to how close I can get the slopes of these secant lines to that number f prime of a by making h sufficiently small, right? If you say get these numbers within 1 over 1,000 of each other, I can find an h. Maybe h is like 0.02 or something that does that. If you say make it within 1 over a billion, I can make h 0.0004 or something like that, and then they will be within 1 over a billion of each other. And so what this is saying is that I can precisely that I can by making h small, I can make f of a, and we're just sort of multiplying through by the h here, I can make f of a plus h minus f of a, the increment, squiggly equals to h times f prime of a. So approximately equal, right? For small h, those things are basically equal. And so what this is saying is that let me do it in maybe orange, that this distance, and that's green, that this distance here is going to 0, right? The distance between the points on the graph and the points on the tangent line is going to 0. And this f prime of a times h, this of course is how much we go over. That's this distance here, that's f prime of a times h, how much we go up on the tangent line when you go over by h, because f prime of a is the slope of the tangent line. So this is what we're using to solve the problem, right? This is what we're being asked to do here, is we're going to say, okay, well, if I want to know what is the third root of 4, right, I'm going to look at this function, third root of x, and I'm going to say I can get pretty close to the third root of 4. So third root of 4 is going to be whatever, if this is 4, and that's third root of 4. Well, suppose I can't find that explicitly. What I can do is I can take a point nearby. So I can take 4 plus delta x, or 4 plus h, whatever you want to call it, 4 plus h, and I can get the tangent line at this point. This is the tangent line at 4 plus delta x as a function of x, and this is going to give me a pretty good approximation. If I look at the value of the tangent line at that point, it's going to be very close to the graph of the function, and so that's my approximation. And over here we could do this, and so the idea was that we wanted to get this at 2 different points, right? So I'm going to do one here and one there, and then I'm going to think about which one is a better approximation, right? So I can do one on either side, and we'll think about which one is a better approximation and why. And that's I think the sort of bonus thing for the question is when does the one on the tangent line that I make using a point on the left become better than the approximation that I get using a point to the right? And so we'll think about that sort of question as we do this. But the points that we were sort of hoping were going to be used were the points. So if that's 4, we're going to have 2 different values of what we're going to call a here. We're going to have a is equal to 1 and a is equal to 8. And let me maybe do these in different colors. Let's do a is equal to 8. And we like these because they're perfect cubes, right? So I know that if this is 8 here, right, then this point is the third root of 8, which is just 2. So I have the point here. I'll put it under the graph because I'm going to draw the tangent line above it. This is going to be 8, 2, and I'm going to come up with the equation of the tangent line at that point and use that to third time's the charm. There we go. And I'm going to use this as an approximation. I'm going to find the point. I'm going to plug 4 into the equation of that tangent line and try to find and figure out what that value is and use that as my approximation for the third root of 4. And same thing, we're going to go here and say if this is 1, well, this point is also 1 because third root of 1 is 1. And so this is the point, I'll do it onto the graph again to save space, 1, 1. And I'll draw the line here and see which one is a better approximation. I've done this graph by hand, so we don't actually know yet whether the purple line is actually above the pink line at that point or not, whether the tangent line at 1, 1 is actually below the tangent line at 8, 2 or not. Because this is just how I drew it, and it could be off. So we're gonna figure that out by actually constructing these lines. It's really, really important, by the way, not to sort of subconsciously, when you're drawing a picture to model the problem, assume that facets of the picture are accurate. It's really easy once you've got something on the page to sort of forget that you just drew it by hand and it doesn't have to be accurate. Always keep in mind what you actually know, what you can actually know or deduce in some way is true. That's definitely burned me on tests and problem sets before. It's super annoying to find out after the fact, but okay. So the first thing I want to do is find the tangent line at at a is equal to, and I'll come up with the calculations down here so we have some space. When a is equal to 8, the tangent line to the graph of f at the point 8 as a function of x is of course going to be f prime of 8 times x minus 8 plus f of 8. And so I need to figure out what is f prime of 8. Well, f prime of x is, well, third root of x prime, which is x to the 1 over 3 prime, which is 1 over 3 x to the negative 2 over 3. So if I plug in 8 to that, f prime of 8 is 1 over 3 times 8 to the negative 2 over 3, which is 1 over 3 times 1 over 8 to the 2 over 3, which is 1 over 3 times 1 over 8 to the 1 over 3 squared. Right? When I'm multiplying exponents, it's like exponentiating the exponents, right? So a to the power of b times c is a to the b to the c, etc. And a to the 1 over b is the bth root of a. These are just our exponent rules at work here. And negative exponents are like dividing. So just in case people were wondering where this is coming from, I get 1 over 3. Third root of 8 is 2, so that's times 1 over 2 squared. So that's 1 over 3 times 1 over 4, which is 1 over 12. So after all this, we get f prime of 8 is 1 over 12. Right, so this is 1 over 12 times x minus 8 plus f of 8 we've already seen is 2. And so this is the equation of our tangent line. So I can go back up here and say that the equation of this is 1 over 12 x minus 8 plus 2. And you can FOIL this out if you want. You can say that this is, not FOIL, you can just distribute it out. This is x over 12 minus 8 over 12. Those 4s are going to cancel. It's going to be minus 2 over 3 plus 2, and 2 is, of course, 6 over 3. So I can add that to the 2 over 3 and make that x over 12 plus 4 over 3, if I want. It does not matter, though. So that's the equation of this tangent line. And so the way the tangent line at 8 of x is this. And so I can approximate the function by plugging 4 into this, right? So I get an approximation, which is going to be t sub 8 of 4, which is 1 over 12 times 4 minus 8 plus 2. 4 minus 8 is, of course, negative 4 over 12, becomes negative 1 over 3, because it's negative 4 over 4 times 3, the 4's cancel. We get negative 1 over 3 plus 2, which is negative 1 over 3 plus 6 over 3. So this is going to be 5 over 3 is the approximation that we get from this, right? So this, and what that's saying is that this point, the y value of this point is 5 over 3. I can do it a little bit neater there. The y value is 5 over 3. So that's the approximation that we get from this. Actually, let me leave the equation on the line there. And so now we're going to do the same thing for a is equal to 1. So on the other side, and see if we get a better or worse approximation. And then we're going to think about sort of why one is better than the other, or vice versa. And then think about, I think the bonus question is, at what point does it switch? So as we're moving sort of from the left to the right, when do the tangent lines start becoming better approximations or worse approximations? I think it was something like that. Hopefully as we do the analysis, it will become clear sort of what the question was. Because there'll be something blatant going on there. Okay, so now we're going to do the same thing for 1, 1, right? The tangent line to the graph at 1 as a function of x is f prime of 1 times x minus 1 plus f of 1. And again, f prime of x is x to the 1 over 3 prime, which is 1 over 3 x to the negative 2 over 3 by the power rule, which is, I'll just maybe keep going over this way, which is 1 over 3 x to the 2 over 3. At 1, x to the 2 over 3 is 1, so we plug in 1, it's 1 over 3, 1 to the 2 over 3, which is 1, so this just becomes 1 over 3. So the slope of this line is 1 over 3 times x minus 1 plus f of 1 is 1, right? Third root of 1 is 1. So this becomes our tangent line at the point. And I'll bring this, actually I'm not going to bring it up because we don't have space. I'm just going to completely take that back and say, all right, this is the tangent line. And now we're going to do the same thing, right? So this is our tangent line, which I might change in just a second if it ends up being above there. But we're going to look for this point on the line, which our approximation using this line, and we do that by plugging in 4. So t of f at 1 of 4 is 1 over 3 times 4 minus 1 plus 1, that's going to be 3 over 3, so 1 plus 1, which is 2. And 2, of course, is 6 over 3. So yes, it turns out that my drawing is not great. This thing is supposed to be, well, I want to leave that though. This dot is supposed to be slightly above there. So I'm going to sort of just pretend that I got this right. Can I tilt this actually a little bit to make it sort of, that's a little bit better. There we go. Okay. I'm just going to pretend this is what it looked like all along. So this is 6 over 3. And so one thing to note, so it definitely looks like 5 over 3 is a better approximation, right? Because this is below, so the third root of 4. By the way, how did I know that these tangent lines are going to be above the graph, that they're going to be overestimates? Well, as you can see from the graph, it is concave down, right? The graph lies below its tangent lines. And we'll be talking about concavity and things like that more in depth as the course goes on. What that means is that the second derivative is positive on that interval. Over here, to the left of 0, the second derivative is going to be negative, and the graph will be above its tangent lines. It's now concave up here. There we go. So that's how we know that it's an overestimate. and so the lower one is going to be the better estimate. So now the question is going to become why is it a better estimate? Because this is the thing, right? Is that one is much closer, or not much closer, but significantly closer than 8, right? This is a distance of 3. This is a distance of 4. So why are we getting a better, by going farther away, right? Why are we getting a better approximation than being closer? And so actually, I think this is a good thing to leave for you all to think about for tutorial. And if you have some ideas about this, you can maybe raise those in the tutorial or send an email or something. But I think this is a great thing to sort of, now that you've seen this much of it, right now we've seen how to do it, and we have this picture, let's ponder over why the tangent line from on the right side there is a better approximation than the one on the left there, and then sort of if you, how far to the left or to the right would you have to go before it's worse, right? How far to the left you have to go, so if I come from the left, if I were to say move this, and this is the kind of things that we think about when we do these sort of problems, if I move this over here, right, can I get a better approximation? I mean, the way I drew it there, it definitely looks like a better approximation, but the idea is, can I move this pink point to the right towards 4 until I get a better approximation than I got from the one on the right? How far would I have to move it? And how far away from the point would I have to move this one on the right before I got a worse approximation, right? Is there a way that you can figure that out? Is there a point at which coming from the left it becomes better than any particular point on the right, or vice versa? So I don't think that's exactly the question. I think it was something about exactly where it switches. I'll sort of revisit that before the tutorial on Friday. But these are the kind of things to be thinking about. So ponder on that, and ponder on that bonus marks question. Keeping in mind that, and I'm not saying this having seen any future quizzes or tests or anything, but keeping in mind that whenever there's a problem that causes people trouble, and I think people had difficulty with this. I know this is the kind of thing that I used to have difficulty with when I did first year calculus. It's one of the trickier, sort of weirder topics in calculus, or at least I found it to be, differential analysis and estimations. Whenever there's a particular tricky sort of problem topic, that tends to be repeated in courses. Professors tend to know about this and keep putting it on stuff until people get it. So this is a really good thing to think about. And of course, because you're engineers, you're going to be doing applied problems, lots and lots of applied problems. And this is one of the applications of calculus. This is actually an application. You might be doing something where you want to find the value of a particular function, but for whatever sort of logistical reason you can't. But you can come up with a tangent line at points close to it and approximate it, and then the question becomes, you want as good an approximation as you get, where should you put the tangent line? Are there better or worse places to put the tangent line? So do think about those things, and I hope this clarified at least what we're doing and how we're doing it, and gives you something to think about for Friday.